Hi, so today we're going to talk about the currency exchange problem, which is a problem that can be solved by dynamic optimization. So let me first try to explain the problem. So for the currency exchange, we are given an amount of money, let's say M, for example 11, and we're given a set of coins. Okay, so for example, this could be a 1 cent coin and a 5 cent coin, and maybe something special like a 7 cent coin. Okay, and we are asked to exchange the amount 11, right? So using coins of 11, 5, and 7. Okay, so basically make amount of 11 cents using coins of 1, 5, and 7 cents. And the problem is to use the minimum amount of coins. Okay. Of coins to do this. So for example, to get to 11, I could use 11 1 cents, okay, which will make the total number of coins equal to 11. However, I could be more efficient and, for example, give a 7 cent and then 4 ones, okay. This would only make 5 coins. And of course, I think you can already see actually the most efficient one is to use 2 5 cents and 1 1 cent, which makes a total of 3 coins. Okay, so the problem is in general, given a list of coins, right? I will call this CI, I1 to N. Okay, you can note it by this, and given an amount M. So the question is, using coins from this set here, CI, what's the minimum amount of coins that I need in order to make the amount M? Okay, and we would like to write this as a Bellman equation. So V is going to be, or Bellman equation is going to give the minimum number of coins to make up a certain amount M. And now, of course, for a Bellman equation, you have to think of the state. What's the state of the system? And here it's pretty simple. So we will use M, or the amount that you would like to make as a state of the system. Okay, and you would like to write it as a maximization or minimization or some function of V's of some smaller problems. And here, smaller problems will be lower amounts of money. Okay, so let's think a little bit what we would like to do. So a brute force approach, for example, would be to go over all possible combinations of 1, 5, and 7 cents, try to come up with all the combinations that make up 11 cents, and then find the one with the fewest amount of coins, right? This is clearly not efficient. The dynamic programming approach is a bit more sophisticated in the sense that you can think of yourself, okay, look, I'm having to return an amount of M. How can I do this? Well, the first small step could be to think of, okay, I can, for example, use a 1 cent. Okay, so if I use a 1 cent, then I use one coin, which is the 1 cent coin, and then I have to return an amount M minus 1, right? Because I already paid with the 1 cent. And what's the least number of coins that I can use in order to repay M minus 1? Well, this is equal to V times M minus 1. Okay, so if I use the 1 cent, then my total number of coins that I return is 1 plus V M minus 1. And this is already efficient because I assume that I already solved the problem for lower amounts. Okay, I can also use the 5 cent, right? Then I will use one coin, which is a 5 cent, plus V M minus 5. Okay, this is the 5 cent, so the amount of money that I have to return after using the 5 cent is only M minus 5. Or I can use the 7 cent, and then I'm going to reduce V M minus 7. Okay, basically what is my goal? My goal is to minimize the number of coins to repay M. So I'm basically going to pick the minimum of these three numbers. So there's one thing that you have to take care of, is that M minus 1, M minus 5, and M minus 7 are going to be well defined, right? So this means that m is going to be bigger than 1 here, m is going to be bigger than 5 here, and m is going to be bigger than 7 here. Right, so I basically only consider this as an option if m is greater or equal to 1, if m is greater or equal to 5 here for the second, and here if m is greater or equal to 7 for the third. Right, so you have some conditions that need to be satisfied, but in general this is how the Bellman equation is going to look like. So in general, if I have a set of coins Ci and an amount of m, what does my Bellman equation looks like? Well, it has the following form, right? I have Vm is going to be the minimum over all possible coins Ci of 1 plus Vm minus Ci. And of course, I'm only going to look for the Ci's that are less or equal to m. Okay, so this is my Bellman equation. It writes the problem of Vm in terms of smaller problems here. And I need to start from a base case. So basically my base case is where m is the starting point for m. So this is going to be equal to V0. So what's the minimum number of coins that I need to use in order to pay an amount of 0? Well, it's going to be 0. Okay, so this is going to be my base case. Okay, so this is basically how I'm going to solve the problem. So let's consider the example that I have shown here. So principle, how can we solve this problem? Okay, so let me make up a table. So what I'm going to do is in the columns I'm going to put the coins 1, 5 and 7. Okay, and in the rows I'm going to use the amount m that I'm gonna have to repay, right? So this is 0 to start with, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is going to be a long table. And let me here at the last row, let me write the optimal number of coins that I need to use to repay the amount m. So if m is equal to 0, well then I'm at my base case. So V0 is equal to 0. It's impossible to use a 1 coin, impossible to use this 5 and a 7 coin here. Okay. So if the amount of money that I need to pay back is equal to 1, well then I can use my 1 coin, right? So I will have 1 coin used, and then I have to repay an amount of 0, and here the optimal number of coins used was equal to 0, so I'm going to have to use 1 coin. I can't use 5 coins to pay back 1, and I cannot use a 7-cent coin to pay back 1. Here for 2, if I use the 1 coin, the last coin that I use is going to be, it's going to be equal to 1, and I still have to repay back 1 coin, and already have used 1 coin here, right? So here it's equal to 1. So it's going to be 1 plus 1, which is going to be equal to 2. So for here 2, I cannot use the 5, I cannot use the 7, so the minimum number of coins that I need to use is equal to 2, which is this number here. If I need to repay 3 coins, I can use the 1-cent coin, then I still have to use 2 coins to repay 2, so this is going to be equal to 3. So all these base cases are very boring because I can only use 1 coin. Right, so I use 3 coins here to pay back 4. I'm gonna have to use 4 coins. Now 5 is a more interesting case. If I use a 1 coin, I still need to repay 4, so it's 4 plus 1 is going to be equal to 5 coins used. If I use a 5 coin, then I have an amount of 0 left to pay, right? So it's 0 plus 1, so I only use 1 coin here, and I cannot use the 7 coins. Okay, so the minimum of 5 and 1 is equal to 1 here. Right, so I have a new optimum. So here, these were the optima, and this is now my optimum choice. If I have a 6, I can use a 1-cent coin. Then I still have to repay 5, and for this I can use 1 coin. So here it's equal to 2. If I use a 5 coin, I use 1 5 coin, and then still need to repay an amount of 1, for which I use 1 coin. So it's also equal to coins, and I cannot use a 7. Okay, so here the optimum is equal to 2. to repay an amount of 7. If I use a coin of 1 cent, I still need to pay back 6. So 1 coin plus 2 coins is 3 coins in total. If I use a coin of 5, I still need to repay 2, which uses 2 coins, so this is 3 coins in total, but here I can use my 7 coin, right? And then I have to repay 0. So here the minimum of these 3 numbers is 1, so I will use my 7 coin, which seems obvious. Alright, so for 8, if I use my 1 cent coin, I still need to repay 7, which I can do with 1 coin, so I have 2 in total. If I use the 5 coin, I still have to repay 3, for which I use 3 coins, so this will make me 4 coins in total. If I use a 7 coin, I still need to repay 1, which is 1, plus a 7 coin, which is 2. So I use the minimum of 2, 4, and 2, which is 2 coins in total. For the 9, if I use a 1 cent coin, I still need to repay 8, which takes 2 coins, so 3 coins in total. If I use my 5 coin, I still have an amount of 4 to repay, which uses 4 coins, so this will be 5 coins in total. If I use my 7 coin, I still need to repay 2, so it's going to be 2 plus 1 is 3 in total. Okay, so here this optimal number of coins is 3. For the 10, if I use my 1 coin, I have 4 coins in total. If I use my 5 coin, I still need to repay 5, which is going to take 1 coin, so this is 2 coins. If I use my 7 coin, I still have to repay 3, which uses 3 coins, so this is 4 in total. So here the minimum number of coins is going to be equal to 2. Okay, so 10 can be repaid by 5 and 5, so this is 2 coins. And here for the last row, my 11, if I use the 1 cent coin, I have 2 coins plus 1, which is 3. If I use my 5 coin, I still need to repay 6, which uses 2 coins, so this is 3. And if I use my 7 coin, I still need to repay 4, so this is 4 plus 5. So here the minimum is equal to 3 coins, right? And if you have more coins, you just make this table wider. If you have bigger amounts, you just make this table longer. Okay, and now I can trace back, so I have 3 coins. I can use a coin of 2, right? Then I have to repay 10. For 10 I use a coin of 5, and then I have 5 left, so I use a coin of 5, right? So this is going to be my optimal coins is going to be a 1 cent coin, a 5 cent coin, and a 5 cent coin, 3 coins in total. So you can also think about the computational complexity of this problem. So what you have to do, so for every amount m, you have to do a calculation, right? So you have to do m times a calculation. And what do you need to do? Well, you need to compute a couple of numbers and take the minimum. Okay, so how many numbers do you need to compute? Well, basically you need to compute depending on the number of coins. Okay, so m, the amount, times the number of coins, which is denoted by n. And then you have to take the minimum, right? So here the complexity is of the order m times n, where m is the total amount and n is the number of coins used. All right, let's see how we can use this in software, how we can program this problem. Okay, so welcome here in Julia. So I made a vector that stores the value of the different coins that I have. So I have a 1 cent coin, a 3 cent coin, and a 5 cent coin. And I'm going to make a function that's called currency exchange, and it's going to take this vector of coins and an amount m, and it's going to give me the minimum number of coins that I need to use in order to pay back m. So first of all, let me also store the length of this vector coin, so I know how many coins that I have at my disposal, and I'm going to store the value in 2 dictionaries. So the first dictionary, for every amount of money, it's going to give me the minimum number of coins that I need to use. And I also want to store the optimal solution, so for every amount of money, it's going to give me a distribution over the coins that is optimal. So I'm going to store this in a vector of And so for example, if I have the vector 2, 1, 1, then this means that I need to use 2 coins of 1 cent, 1 coin of 3 cents, and here 1 coin of 5 cents. Okay, so this is how I'm going to store the solution. And I'm going to return V and exchange. Okay, and then I'm going to call the value currency exchange for coins. Okay, and for some amount, let's call it 11. Okay, and now I'm just returning to empty dictionary, so nothing much happens. So first let me look at the base case. When I have 0 amount of money to return, then I'm going to use 0 coins. Okay, and my optimal vector of coins is going to be equal to the zeros vector, right? So vector of size n with all zeros. So what I'm going to do, I'm going to build my table row by row. So for amount, let me call the variable amount 1 to m. So the Bellman equation, let's think back, was v of amount was the minimum. I take the minimum over the value of all possible coins of 1 plus vm minus ci. Okay, subject to ci being less or equal to m. Okay, this is a constraint that you have to take into account. So basically what I'm going to do is I'm going to loop over all possible coins. I'm going to compute this and then take the minimum. Okay, and I'm going to store all these possible values in a vector. Let's call it vector temp. I'm going to initialize it as a vector of zeros of size n. I'm going to store all these values in this vector and then minimize this vector. Okay, so for I equal 1 to n, so I'm looping here over all coins. Well, first of all, if this constraint is not satisfied, so this means that coins I is bigger than amount. This should not be m, but amount. And here also. Okay, then I know this is not feasible, so I don't want this to be the solution of my minimization problem. So I would just put temp I to be equal to some very big number. Okay, so there should be an if condition here and here. Else, if the constraint is feasible, then temp I is going to be equal to 1 plus v of amount minus the value of the coin. Okay, which is this thing here. Okay, I'm going to end this iteration, and now I have my vector of temp, which is going to store all these values here. So I'm going to go use the function findMin of temp, and this returns 2 numbers. The first one is going to be the value, that's the minimum. So this is what I want to store in v amount. And then the second one is going to give you the position at which it finds the minimum. So this is going to be the index of my optimal coin. Okay. I'm going to use this index in order to update the exchange here. Okay. So previously I have to look at the exchange of amount minus coins opt coin, right? This was the optimal value here. Okay, let me store this. I'm going to make this new vector in 2 steps. So first I'm going to store the previous optimal value, and then I'm going to add 1 to this optimal coin. Okay, exchange amount at position opt coin. I'm going to add 1 to this here. Okay, this is how I'm going to do this. So first I take the vector that was optimal before using the last coin, and then I'm going to add 1 value to the last coin that I used. So there's one trick here, Julia. If you use an assignment, then basically what you're doing is, what you want to do is make a new vector and copy every element of this vector into this new vector here. But this is not what Julia now is doing, because it's basically you're just using assignment, which means that you're going to give this vector a new name. So every time you change this vector, you're also going to change this vector, right? So in order to avoid this, you have to use the copy command in Julia and also in Python, by the way. So this is a small fix that you will need to use. So if I now compile this, it gives you an error. So apparently I forgot an end. Yes, there should be an additional end here. So now it compiles. And if I run this, I have to find the minimum, not just to find anything, right? So now it compiles, okay? So for example, if I have total amount of 11, I have to use 3 coins. And if I then look at which coins I need to use, I can use 1 coin of 1 cent and 2 coins of 5 cents. And of course I can increase, I can for example store the solution to vector v, dictionary v and dictionary exchange, and I can change the amount. So for example, what coins should I use when I have the total amount of 26 is 1 coin of 1 cent and 5 coins of 5 cents. And of course I can also update the coins at my availability. So for example, if I make a strange coin of 11 cents, I don't think this exists, but anyway, if I then compute the new optimal solution, I will use 2 coins of 11 cents, 1 coin of 3 cents and 1 coin of 1 cent, total amount of 4 coins in order to pay an amount of 26. Okay, so this was optimal currency exchange. Thank you for watching.